Hi everyone, welcome. അപ്പോൾ നമ്മൾ ഇന്ന് ഡിസ്കസ് ചെയ്യാൻ പോകുന്നത് some of the previous year questions of electrochemistry from various competitive examinations. Okay, so the first question is on the screen. Question ഇതാണ്: the correct value of E naught, which is standard electrode potential of a half cell in the following graph of E, the potential, versus log M, molality, where M stands for the concentration, S. Graph depict ചെയ്തിട്ടുണ്ട് and there are four options which are given. Okay, so നമ്മുടെ അടുത്ത് standard electrode potential ചോദിക്കുകയാണെങ്കിൽ there are two ways in which we can find that. One is E naught of the cell is equal to E naught of the cathode minus E naught of the anode. Now, please note, whenever you use this equation, it is always the standard reduction potentials of the anode and the cathode that we use. This is an equation. So, ഇവിടെ നമ്മുടെ LHS ഉള്ളത് standard electrode potential of the cell ആണ്, whole cell, where cathode will form the reduction half cell and anode will form the oxidation half cell. This is one equation. നമ്മുടെ അടുത്ത് ചോദിച്ചിരിക്കുന്നത് standard electrode potential കാണണം of a half cell where E versus concentration the term വരുന്നുണ്ട്. So there we'll be using the very famous Nernst equation. Nernst equation expression ഇങ്ങനെയാണ്. It is Nernst equation. Okay. So this is the equation that we should use. എങ്ങനെയാണ് നമ്മൾ Nernst equation ആണ് യൂസ് ചെയ്യാന്ന് അറിയുന്നത്? It is this relation of standard electrode potential of the cell, and it should have concentration term in it. അപ്പോൾ ഈ രണ്ട് കാര്യങ്ങൾ റിലേറ്റ് ചെയ്തിട്ടാണ് നമുക്ക് മനസ്സിലാകേണ്ടത് that the equation that we should employ here is that of Nernst equation. Okay, so the equation is like this. It is E cell is equal to E naught of the cell minus RT by NF ln concentration, okay, concentration of the oxidized species by concentration of the reduced species, depending upon the reaction which was given. Okay, so this is the equation where E cell is the potential of the cell at any condition. E naught of the cell is the standard electrode potential, and that's what they have asked for. R is the universal gas constant. T is the temperature at which the potential is measured. N is the number of electrons which are used or which is being participated in the reaction. And F is 1 Faraday, which is approximately 96,500 coulomb and accurately 96,485 coulombs. So instead of general expression where in the numerator you have the concentration of the oxidized species, and denominator you have the concentration of the reduced species. So instead of this ratio, they have just mentioned M. Ratio of the concentrations in avare M ennaanu represent cheyidirikkunnu. So we can also do the same. M. Okay, so this is the Nernst equation. This is what we are going to employ. Now, idine oru graphical form ilekku aakumbo, what would be the situation? Now, this is the form, and the graph what they have given is linear. It is linear, right? Appo linear aayittu namukku graph kittumbo, we should know that the linear graphs are usually written in the form of y is equal to mx plus c, where y is y-axis il nammal endanu notate cheyyunnathu, that is the y, that is represented as y here. So y-axis il ivide enda, it is E cell. Okay, so this corresponds to y. All right, and c is the intercept. C is the intercept. So intercept means nammade line or the curve which was given to you, y-axis il evideyano intersect cheyyunnathu, that is the intercept, y-intercept. C is specifically, this is y-intercept. Y-intercept. Okay, so namukku ivide ullathu നമ്മുടെ ഇക്വേഷൻ നമ്മൾ y is equal to mx plus c എന്ന് പറയുന്ന ഒരു ജനറൽ ഇക്വേഷൻ ആയിട്ട് കമ്പയർ ചെയ്യുകയാണെങ്കിൽ what you have is E cell, that will be y. And what is the intercept? Intercept from this equation, C, if you just relate this, this is y is equal to intercept. Okay? Intercept ഇവിടെ വരിക standard electrode potential ആണ്. Now how is that? We'll just check the next term so that you will understand that too. ഇവിടെ x-axis ഉള്ളത് log m ആണ്. That means this will be forming the x-axis. Okay, so this is y, this is x. X ന്റെ കൂടെ associated നിൽക്കുന്നത് m ആയിരിക്കും. So the remaining, which is the term which is remaining here, would be c. So what we have here is y is equal to c minus mx എന്ന് പറഞ്ഞൊരു ഫോർമുല ആണ് നമ്മുടെ ഗ്രാഫ് കിടക്കുന്നത്. That's all right, because this could be the positive or minus and intercept can also be positive or minus. നമുക്ക് ഇവിടെ ഉള്ളത് c minus mx ആണ്. That's all. So the intercept what we have here is E naught of the cell. That is E naught of the cell, and that is what they have asked in the question. E naught of the cell, E graph il namukku engane kitta? It is the C intercept. Sorry, it is the Y intercept. It is C, the Y intercept. And what is the point, or how will the Y intercept is represented in the option? It is B B dash. That's all. Option C, B B dash. Okay. So from this question, we are able to learn two equations. That is E naught of the whole cell comprising of oxidation as well as reduction. Half cell is this, where standard reduction potential of the cell is determined by this equation. Please note that നമ്മൾ ഈ equation 1 എന്ന ലേബൽ ചെയ്തിരിക്കുന്ന equation employ ചെയ്യുമ്പോൾ it should always be the standard reduction potentials that we are using. Okay, and the second one is the Nernst equation, very famous Nernst equation. Okay. Now, just in case of confusion, we have written it in the terms of ln m. You can convert it to log, no problem. Just one more equation so that ln and log akam, it is like this, that's all. E cell is equal to E naught cell minus 2.303 RT by NF log m. This is just the extension of this equation. Okay, now this you can further shorten this equation like this. E cell is equal to E naught cell minus 0.0591 by n log m. Now these are all the expression for the very same Nernst equation. എപ്പോഴാണ് നമുക്ക് ഇത് 0.0591 കിട്ടുക ചോദിച്ചാൽ it is when temperature is 25 degrees Celsius, okay, corresponding to 298 Kelvin. F we know it is 96,485 coulombs, and R is 8.314 joule per Kelvin per mole. Now, all these are constant. Substitute this is what you have. Okay, so in the graph which is given to you, this is the x-axis. This is taken as the x-axis. This is taken as the y-axis. X would associated will be the slope. So the slope of the graph is this. This would be the slope, and the question is indirectly intercept endaanunulladana. This is the intercept. Question, E naught of the cell enginanu represent cheyanulladana. So it's just the ulta. It is the Y intercept is E naught of the cell. That's all. Okay, I hope this is clear. Now this is the second question. It's a very good question. Which one of the following conductometric titrations will show a linear increase of the conductance with the volume of the titrant added up to the breakpoint and almost constant conductance afterwards? Now, see, first of all, conductometric titrations, these are titrations wherein we measure the end point of the titration via observing the jump in the conductance value. That is what we measure here. So there will be a sudden change in the values of conductance. That is one point. Now, the next point is volume of the titrant added up to the breakpoint and an almost constant conductance afterwards. So that is the first hint which is given in the question. In the end point usually what we do is you take the acid in the conical flask, and the burette is filled with the base, and that is what is known as the titrant. Idana titrant. Okay, Now what is given? End point എത്തിക്കഴിഞ്ഞിട്ട് എന്ന് വെച്ചാൽ ഫ്ലാസ്കിലുള്ള ആസിഡ് എല്ലാം ന്യൂട്രലൈസ് ആയി കഴിഞ്ഞു. അതിനുശേഷം when you add excess titrant to it, the conductance is almost constant അത്രേ. എന്ന് വെച്ചാൽ the base which is coming into the flask is only partially being dissociated. ശരിയല്ലേ? Because for conductance what we need is number of ions must increase. Number of ions titrant നമ്മൾ ആഡ് ചെയ്തിട്ട് പോലും ions ഉണ്ടാകുന്നില്ല എന്നുള്ളതാണ് ഈ ഒരു കോൺസ്റ്റന്റ് കണ്ടക്ടൻസ് എന്ന് പറഞ്ഞ ടേം സൂചിപ്പിക്കുന്നത്. So the first hint that you'll get here is the titrant which is being used is not at all strong. Strong as NaOH ആണെങ്കിൽ it will rapidly being dissociated into, it will rapidly be dissociated to Na plus and OH minus. So that's not happening here. So what they are saying is the conductance is constant. Constant ആണെങ്കിൽ അവിടെ നമ്മൾ യൂസ് ചെയ്യുന്ന base would be very weak. So let's say it's ammonium hydroxide. So ammonium hydroxide in ഒരു പ്രത്യേകത എന്താണെന്ന് ചോദിച്ചാൽ it's a very weak base. As a result dissociation ഉണ്ടാവുന്നില്ല എന്നുള്ളതല്ല, but then it is very very low. The degree of dissociation for ammonium hydroxide is low. As a result we get a constant conductance after the end point. So ഈ ഒരു hint വെച്ചിട്ട് we can avoid two options, A and C. Why A and C? Because they are using a strong base. This is also a strong base. Okay. Now the next thing is രണ്ട് കാര്യങ്ങളാണ് തന്നിരിക്കുന്നത്. ഒന്ന് a strong acid with a weak base and രണ്ട് a weak acid with a weak base. Now for that this is also easy. Now let's take the first case where you have this is conductance along y-axis and this is the volume of titrant and ours is a weak base, so I'm just writing it as ammonium hydroxide. Okay, the strong acid ആണ് നമ്മൾ യൂസ് ചെയ്യുന്നെങ്കിൽ let's say it is HCl plus NH4OH. This is the reaction which is happening here. So conical flask you have HCl which is very strong and അവിടെ H plus is definitely HCl എന്ന് പറയുന്നത് H plus and Cl minus ആയിട്ടായിരിക്കും exist ചെയ്യുന്നുണ്ടാവുക. So there are ample numbers of H plus in the conical flask initially. When you keep on adding this titrant, NH4OH which is a weak base, അത് OH വരും as a result of partial dissociation, right? So this along with the OH minus of the weak base will combine, H plus and OH minus of the weak base will combine to give water. Now what is happening here? H plus and OH minus combine ചെയ്ത് water ആവുന്നതിന്റെ ഫലമായിട്ട് the number of H plus ions in the flask കുറഞ്ഞുകൊണ്ടിരിക്കുകയാണ്. So when this current carrier അതിന്റെ concentration കുറയുന്നതിന്റെ ഫലമായിട്ട് the conductance will decrease. It will keep on decreasing. എത്ര നേരം ഇങ്ങനെ കുറയും? This decrease is observed until the concentration of H plus is almost complete. Okay, and after that what will be happening? Further addition of NH4OH to this mixture will change the conductance value almost like this. കുറച്ച് വ്യത്യാസം മാത്രമേ ഉണ്ടാവുള്ളൂ. Why? This is because of the partial dissociation. But what you see here is first the conductance value കുറയുന്നു and then more or less no change. നമുക്ക് ഇതല്ല വേണ്ടത്. നമുക്ക് വേണ്ടത് what is അവരുടെ question and the end point ന് മുൻപ് ഒരു linear increase ഉണ്ടായിരിക്കണം. So definitely the answer is option B. Now we'll check that. എങ്ങനെയാണെന്ന് നോക്കാം. So here you have conductance and here you have volume of NH4OH. So now we are going to take a weak acid, okay? So you are taking a weak acid CH3COOH. So this is a weak acid. It will be in equilibrium with CH3COO minus and H plus. Okay? And along with this, we are using ammonium hydroxide as the base. So that would be NH4OH in equilibrium with NH4 plus plus OH minus. All right. So initially, what is the case? You have H plus ions in the flask. It will combine with OH minus. As a result, water molecules are being produced. Avade conductance in the value കുറയും. After a particular point, what will be happening? H plus ellam consume idu kazhinju, but then there are also undissociated CH3COOH molecules present. So there, what will happen is CH3COOH will combine with NH4OH, and this will give CH3COONH4. This is formed, and which is a salt. Now, what is the what is the speciality of the salt? The salt which is formed is completely getting dissociated to CH3COO minus and NH4 plus. Now, we arrows is Radhikanam. Even we have put an equilibrium because it is weak. This acid is weak, this base is weak. Even we haven't used an equilibrium arrow. This is direct. That means e salt at completely in the ions produce in the. So whenever you have number of ions increasing in the flask, definitely it will lead to an increase in the conductance. So even till the next point, the conductance will increase. Etra neram increase until the salt is formed. Etra neram is salt to form until acid is present. So once this acid is over, it is quenched, the salt formation will be stopped, and that is the end point. This is the end point. Now, further addition of NH4OH to this will more or less change the conductance. So this is the graph. All right. So it's option D. Now, from this portion, this is a detailed explanation of this question. Moving on, question 3. Again, confusion because what they have asked is about Colbrash's law. Colbrash's law is applicable to a dilute solution of. They have given 4 options. Before reading the options, I would like to say just one point. Colbrash's law is meant for strong electrolytes. It is for strong electrolytes. Yes, we do apply things in the weak electrolytes, but it's just the assumptions and the results of the strong electrolytes that we are applying in the weak electrolytes. So please have in mind that strong electrolytes in the Colbrash's law define. So now we will check the options. Another options, it is potassium chloride and hexane. So here, what is happening? Potassium chloride won't be completely soluble in hexane. One is polar and the other one is non-polar. Okay, so it's not A. Acetic acid and water. Acetic acid is weak. So nammal paranju Colbrash's law is for strong electrolytes. So it's not B. Hydrochloric acid in water. Okay, no, that is it. HCl is strong. It is completely soluble in water. So it's option C. It's option C. The last option was benzoic acid in benzene. So benzoic acid is non-polar. It's not completely polar, but then it's not non-polar too. Intermediate aitana benzoic acid in benzene. Definitely it won't work because it's strong alla. So it's not D also. So option C. Okay, so this is the point that we have to learn from this equation. That's all. Question number 4. This is from Latimer diagram. Okay. The standard electrode potentials of what they have given is Fe3 plus bar Fe2 plus. Now, what you have to learn here is Fe3 plus Fe2 plus aganulla potential aanu tannekkunnathu, meaning they have given the reduction potential. Correct? Fe3 plus to Fe2 plus. So, E naught of Fe3 plus bar 2 plus. This is given. Etra plus 0.77 volt. And also they have given the reduction potential when Fe is changing from 2 plus to just plus. That is also given. That is minus 0.44 volt. What they are asking is they need the reduction potential when ion 3 plus is being converted to ion. So we'll check that. It is Latimer diagram. So Latimer diagram, now there are 3 ion, 3 species which are given. And the kya? Fe3 plus, Fe2 plus and the Fe. Okay. So initially, what they have, let's take this as E reduction potential, namukku E naught 1 ആയിട്ട് എടുക്കാം. Fe2 plus Fe ആകുന്നത്, let's take it as E naught 2. What they have asked for is Fe3 plus Fe ആകണം. E naught 3. That is a question. So always remember, reduction potentials are not at all additive in nature. In vechal, E naught 3 is not equal to E naught 1 plus E naught 2. This is not equal. This is not true. But then it is the Gibbs free energy values which are equal. Okay. That is delta G naught 3 is equal to delta G naught 1 plus delta G naught 2. Gibbs free energies are additive in nature. അപ്പൊ നമ്മൾ ഇവിടെ ചെയ്യേണ്ടത് or മനസ്സിലാക്കേണ്ടത് എന്താന്ന് വെച്ചാൽ Fe3 plus നിന്ന് Fe ലേക്ക് മാറുമ്പോൾ there will be a particular amount of Gibbs free energy associated with this reaction. That is equal to delta G naught of 1 plus delta G naught of 2. So these are the two things. Now, what is delta G? How is it related to E naught choicha? Delta G naught is equal to minus NF E naught. That's all. N and the number of electrons which are involved. F and the, it is Faraday, 96,500 coulombs approximately. E naught is a standard electrode potential. That's all. So now we can solve this. Delta G naught 3 is equal to delta G naught 1 plus delta G naught 2. Now we'll put this equation here. Minus NF E naught 3 is equal to, now this is the number of electrons involved here. 3 and represent the reduction potential. So let's write N3 here, okay? Which is equal to minus N corresponding to the first reduction potential, F E naught 1 minus N F E naught 2. Okay. Now please check the number of electrons. E naught 1 in the good associated, it's just one electron. Correct? E naught 2 in the good associated, Fe2 plus Fe agana, so 2 electrons are gained. So that is true, 2 electrons. E naught 3 in the good associated with Fe3 plus Fe agana, so 3 electrons. So now you can rewrite this equation like this. Minus 3F E naught 3 is equal to minus F E naught 1 minus 2F E naught 2. All right. Now F is common, minus is common. Minus, minus, minus. Faraday, Faraday, Faraday. You can cancel that also. So what is it? We have E naught 3 is equal to E naught 1, which is given 0.77 plus 2 into E naught 2 is minus 0.44 volts divided by 3. So this will be 0.77 minus 0.88 divided by 3. That is minus 0.11 by 3. So it would be option minus another C D U and you have minus 0.11 by 3. So it's not C, it's option D. Option D. Yeah. The last question. In a potentiometric titration, the end point is obtained by observing. Now options in there. So conductometric titration, we said that we'll be measuring the jump in conductance. Similarly, in a potentiometric titration, the end point is observed by measuring the jump in potential. Okay, so it's option B. Yes, so that's all for today. Thank you and have a nice day. Bye. See you.